Okay, so I hope that my screen is visible. And so what you did previously was extracting some features because in the image there is a lot of data that is not necessary for a model, and that is unnecessary for us to give it to a deep learning model to actually classify our data. So what we do is we perform some convolution operations on our data or our image, and then that data is then passed to a network or a deep learning network. So what you do is first, like Mohit told you, that you need to flatten our data. The reason that we are flattening our data is because uh, the deep learning neural network cannot actually take 2D data. So for example, after performing convolution and max pooling, you have some kind of 2D data, for example, a 3x3 matrix, and you need to flatten it to actually pass it to this network. So once you pass this to a deep learning network, what it does is it first of all it has some weights on these lines or these connections. And what it does is it actually multiplies the inputs with these weights and then pass it to a neuron or a perceptron in this case. And once these values are passed to this neuron over here, they are added together and then they are passed through a activation function. And that can either lead to the activation of a neuron or a deactivation of a neuron. And that is how you actually classify your data. So in our deep learning models, we have something called a dense layer. So what exactly is a dense layer? So a layer is called a dense layer if it is connected to all the inputs from the previous layers to every neuron in the current layer. So for example, if I have this neuron, it is connected to this one, and the rest of these. And similarly for all the other neurons. And that is also the reason why we call it a dense layer, because every neuron in the previous layer or every output from the previous layer is connected to the every neuron in the current layer. So what this model does is it will perform some kind of calculations, and some of these neurons will be deactivated, some of them will be activated, and that is how classification works. Once like you pass your data through this model, and you will get some kind of output, and this output is usually in form of a softmax function or softmax value if you are performing a classification operation. In this diagram you can see that there is only one output neuron, but in our models we'll be having more than one neurons over here. So a dense layer is nothing but connection of all the neurons from the previous layers to the current layer. And by passing your data through these layers, you can actually perform some kind of classification on the required data. So, okay, so that is the entire working of a convolutional neural network. And the only new part in this is that the introduction of convolution operations. And before that, we only used to have a dense layer or the deep learning models without convolutions. And that used to take up a lot of time and computational power, which we cannot afford to use. So what convolution layer does is it actually reduces the size of our image so that we can pass it to our deep learning model, and we can like classify our data. Okay, so now that we know what a convolution neural network is, let us move on to how we can implement it. So for this tutorial, I'm going to be using the MNIST dataset, which is available in Kira's datasets. And this dataset consists of digits, or it has 0 to 9 digits. And we are going to be classifying these digits based on the images. So we are going to be classifying our images into a set of digits.
So first I'm going to import some libraries, for example, NumPy, TensorFlow, and also the one-hot encoder, Kfold, and all these. And I'll tell you why we need these. So first you need to import the dataset, and you can do that by going to Kira's datasets.mnist.load data.
What this function does is it automatically divides your data into train and test values or train and test data sets, and is quite useful like when you are working like when you are only practicing. Instead, like when you will be working in a real life situation, you'll find that working with data is a lot more harder, and processing your data is much more harder than actually training your model. So I'm going not going to show you how you can process your data. We're going to use the TensorFlow's built-in data set so that we can do it in short amount of time. So once I import this, you can see that it has 6,000 values, 6,000 test images, sorry, 6,000 train images, and test images are around 1,000. And as you can see that the size of our images is in 28 into 28 pixels. And so once you have this, you can take a look at what exactly this input looks like. For example, in this input, you can see that this is a 5, and if you look at the train y, or the actual value for that input, that is 5. So before passing this to our model, we need to tell, our model cannot decide that it is 5 or 6 based on just looking at that image. So what we need to do is we need to encode them into some form, some other forms. For example, we are doing a classification task. So in a classification task, you can only classify either a true or a false. You can say that either a value is true or a false. And to classify a model having more than one inputs or more than one class, we need to actually encode those classes into binary digits or binary form. So what I'm going to do is I'm first going to convert my image into a channeled input. So the reason that I'm doing this is because usually in a real world app, you would be having a you'll be having colored image, and that image has a three channeled input. Or this over here we have a black and white image, so that's why I'm keeping the channel to 1. But if it is a colored image, then the number of channels you have is going to be 3. So I'm just reshaping my data to a channeled input that is 28 into 28 into 1. And that doesn't really change my data much, and it only changes the shape of my input. Okay, so this is the main part. So what I'm doing over here is I'm performing a transform operation on my data, and I'm transforming my data using the one hot encoder. So what one hot encoder does is it will encode our values. For example, if you have 5 classes, then it will convert a single numeric value into this form over here. So so after we run this, you can see that I'm also doing this too dense over here. The reason for doing this is when you perform the one hot encoding, it will give you a sparse matrix, and you cannot really work with sparse matrix in Python. So what we are going to do is we are first going to convert it into a dense matrix. So by the way, sparse matrix is basically a matrix that has values, it will have value in one place, and if all the other values will be empty. So so the way that TensorFlow represents a sparse matrix is that it will give you the location of that value and the value itself. So we need to perform one hot encoding, and then we need to convert our output into a dense output, or so that we can pass it to our machine learning model. So that's all that I am doing over here. And then I'm also doing this step, and what this does is it actually normalizes my data. So so your images consist of 0 to 255 pixels, or different types of pixel color values. What we need to do is we need to normalize it so that our model can recognize the image easier, so that our model has less information to work with. And uh, and also, if you try to look at the input after I normalize it over here, you can see that the minimum value is equals to zero point 0.0, and if I try to look at the max value, it will be 1. As you can see, it's 1. Okay, so now let's build our model. So in Keras, we have this function called sequential, and what this does is it will create a sequential map of your layers. And the way that TensorFlow works is it actually creates graphs of your models and passes your input values through those graphs. So what sequential will do is it will build you a graph using the layers that you pass into it. So so the first layer that we are going to create is a convolution layer. And so this layers comes from the Keras library. So for example, if you look at over here, you can see that I imported the layers from the tensorflow.keras. And inside layers, you will find all the layers that you are going to be using. And in this one, we are going to be using convolution 2D layer. And this is the you can say this is the number of number of maps we want to create, or the number of feature maps we want to create. So right now I have input of size 28 into 28, and it will generate 32 feature maps from this 28 into 28 image. And the activation function that I'm using is ReLU, and the kernel initializer is basically what it does is it serializes your data. And there are a lot of different types of initializers, kernel initializers available in TensorFlow, and if you want, you can take a look at that, but we are not going to go into serializing your data in this tutorial. Okay, so the next step that I'm performing is a max pooling. So like Mohit told you that we need to perform max pooling after the convolution layer, so so as to like extract more data out of your convolutional filters. And then I'm just going to flatten my input, or input to my dense layer, because this will return me a 2D array, but my dense layer can only take a array of a single dimension. So first I'm going to flatten it, then I'm going to use a dense layer to actually train my model to classify different classes of my input, that, and those classes are the digits that we want to classify. And over here, I'm using 100 neurons, or 100 neurons. Once you flatten this, it will go into this dense layer, and then it will generate 100 neurons, 100 output values. And then those 100 output values will be mapped to the 10 values that we want to get. And over here, I'm using a softmax max function because I want to know the probability of a digit actually being the correct digit. So for example, it will return me 10 probabilities, and the one that has the highest probability will be the correct output. So after this, you can take a look at the model summary. So what model dot summary does is it will show you the your model architecture. And as you can see that after max pooling, we have these 5,408 parameters, and these are just like what max pooling does is it basically returns you some value, and then what we do is for example, in this case, it is returning 13 into 13 into 32 metrics. And To flatten this, we are going to convert it into a array of single dimension. So if you try to multiply these values, you will get this output. And the rest is quite simple. So let's move on. And over here, we need to tell the model that how we want to compile our model, or how we want our model to work. For example, over here we have few parameters such as the optimizer, and the optimizer is basically the how you want to optimize your uh, learning rate. So over here we are using a stochastic gradient descent, and in most of the cases you'll be using the optimizer, but in this case we are using the SGD because from the research it was proved that in this case the SGD worked better than Adam. But you can also use Adam optimizer, but that won't make much of a difference because the problem is quite simple. And as for the loss, we are using the categorical cross entropy loss, and we are then getting the matrix called accuracy. And this matrix is used to compare our outputs from our model to the actual outputs, or the actual values. So, so the way that we train our model is we use model.fit, and inside there we pass our inputs and the expected outputs. And then you can tell your model for how many for how many more epochs you want to train it for, and it will it will take quite some time. I think I'm using the CPU for this. That's why it's taking time. Yeah. So the reason that it was taking so much time is because I was using CPU instead of GPU. But if you had used GPU over here, then it will be done much more faster as compared to CPU. And so So, but once you are done with once you are done with your model, or once you are done training your model, you can just use the predict function to check if your model actually works. So I already have these outputs, and my model is still training. So I'm just going to show you this output over here. So the way that you predict your outputs is you pass in a array of inputs that you want to predict inside the model.predict function, and it will return you some array of probabilities. Like over here, we can see that I'm looking at the probability of my first output. So if you look over here, you can see that the highest probability is this one, that is 1. And if you count the number from 0 to 7, it should be 7. For example, 1 2 3 4 5 6 7, sorry, 0 1 2 3 4 5 6 and 7. Yeah, so the output is actually 7. And as you can see from my test, or my the outputs that I previously had, uh, it also returns me 7. So we can say that my model is pretty accurate, and also you can look at the training that the accuracy is around 99%. And this model is quite simple, and you won't be having only a single convolution layer. What In most of the cases, you will have around 3 to 4 convolution layers for simple problems, and for deep learning problems, you'll be using architectures such as ResNets, which have layers around 34 to 127 even. And the the deeper your neural network, or deeper your model is, the greater the accuracy. But it was proved that that is only true up to some limit, and afterwards the accuracy starts dropping. Okay, So as you can see that it still returned me the same output because I was using the same input over here. Okay, so that's it for today's workshop. If you have any questions, you can ask me now.